Welcome to College Algebra, Chapter 1, Section 6, where we're talking about other types of equations. I'll be using some notes that were adapted for Blitzer's College Algebra 5th edition, and I'll talk about some concept, we'll talk about some process, and in this section, we're going to start off looking at some polynomial equations. We've got some different types of polynomial equations. Sometimes they're linear in fashion, where we only have an x to the first power. Sometimes it's a second degree polynomial, where we have an x squared involved in our equation, or a third degree polynomial, where our largest exponent is 3, and so on. So the largest exponent there is telling us the degree of our polynomial. And in example 6 here, we see a request to solve this equation by factoring and the use of the zero product principle. So let's see what we can do. The first thing I would do, as we saw in the previous video or previous section, is balance everything over to one side of the equation so that the other side is equal to 0. And since we have a term that's 9x to the third power, our largest degree term, it's already positive, that positive 9 that's there. I'm going to leave that 9 there, so I'm going to move everything else over to join it on the right hand side. So let's subtract x from both sides and subtract 1 from both sides so that we can zero out the left hand side. Now, as the instructions recommended, let's factor. And very similar to what we saw when we talked about using the AC method, I've got these 4 terms here, and when you've got 4 terms, you're trying to solve an equation, factoring by grouping is a good thing to just glance at the equation and see, does factoring by grouping make any sense? If I do the grouping, do I end up with my first 2 terms, do they have a common factor? Do my second 2 terms have a common factor? If so, then consider moving forward with factoring by grouping. And as you might recall, in the first 2 terms, we're going to factor out the GCF, which is 9x squared. And that leaves us with leftovers of x and positive 1. And we can always check to make sure that we factored correctly by multiplying it back out. So distribute the multiplication in your head, confirm it does indeed equal the original first 2 terms. We're in good shape, let's keep going. We want something to appear here, and then to have another set of parentheses that says the same as the first set of parentheses, x plus 1. And we can make that happen by factoring out a negative 1 from our second group. Again, you can distribute negative 1 to these 2 terms, and you do get the original third and fourth terms from your original equation. Now, same as we did before when solving using the AC method, I'm going to factor again. And I like to take my common factor and write it first. That's the x plus 1. I put my leftovers in their own little piece of Tupperware here. Those leftovers are the 9x squared and the minus 1. And we have 2 factors, 2 sets of parentheses, connected by multiplication, equal to 0. So we can use the zero product principle now. And we'll set this factor equal to 0 and separately the second factor equal to 0. First one is pretty easy to solve. We'll subtract 1 from both sides and get our first solution of x equals negative 1. In the second little equation here, I will add 1 to both sides so that I have 9x squared equals 1. and then I will divide both sides by 9. And then we need to take the square root of both sides. The square root and the square are going to cancel out, leaving us with an x on the left-hand side. And the square root of 1/9 is plus or minus 1/3. Positive 1/3 times positive 1/3 gives us 1/9. Negative 1/3 times negative 1/3 also gives us 1/9. So these are your 3 solutions, and if you're entering these online, you'll probably have to write them as 3 actual separate solutions separated by commas. -1, comma, 1/3, comma, negative 1/3. The next type of equation we want to look at is radical equations. Let me zoom out so that you have access to everything written here. There you go. A radical equation is an equation in which the variable occurs inside of a square root or a cube root or some other higher root. If the index is bigger than 3, that's okay. You can keep going with it. I'll leave you to read what's in this box here if you care to. I'm going to jump right into example number 7 and start solving this equation. The square root is definitely the issue for me in this equation, and I know that the only thing that sort of cancels out a square root symbol is squaring let's say. I'm not just going to immediately square both sides of this, however. First, I'm going to isolate the radical. I'll get that square root symbol all on its own. So maybe I'm going to do this in there are a couple of different ways you could do this to get organized, but what I'm going to do is leave the x over here, and I'm going to keep the 1 here, and I'm going to add the square root of x plus 11 to both sides so that it disappears from the left-hand side and appears on the right-hand side. Then I'm going to subtract positive 1 from both sides. And now I have isolated my radical, the square root symbol. So these 2 steps, we did those in order to isolate the radical or isolate the square root. Now we're going to get rid of that square root symbol by raising both sides to the second power, in other words, squaring both sides. On the left-hand side of this equation, I should be doing x minus 1 in parentheses times x minus 1 in parentheses, FOIL, combined like terms. If you go through that process, you should get x squared minus 2x plus 1. And on the right-hand side, squaring and square rooting cancel each other out, leaving us with x plus 11. Now we're looking at an equation like ones that we've already seen. And that's very typical as we go along learning math, especially as we take one concept and build it into the more complex examples. The solution process usually gets longer because we add additional steps to the beginning of the process. You've already seen problems like this. This stuff up here is the new stuff. So keep an eye out for that and realize that we're building these problems in complexity by adding to the beginning of the process. The initial scenario is more of a pain. Now let's churn through that second part of the process that we're already pretty familiar with. Let's take this quadratic equation and set it equal to 0 by moving everything over, in this case, to the left-hand side. Let's subtract x from both sides and subtract 11 from both sides. Negative 2x minus x makes negative 3x, yep, and 1 minus 11 makes negative 10. We're good. I'm double checking my arithmetic. Arithmetic's not my strong suit. Complex ideas is my strong suit, but very often when I have to do arithmetic, sometimes I'll even sneak over and use a calculator just to make sure I did it right. But on the fly like this, or if I'm cruising through homework, or if it's a test, it's not worth doing the whole rest of this problem if I made a mistake on some very simple arithmetic. So figure out what pace is best for you to keep you as accurate as possible, but still allow you to move forward with the problem. Here's an example of a quadratic where your leading coefficient, your a value, is a 1, and as I've recommended fairly recently, you might just want to sketch out what this thing's going to look like. If I FOIL this, x times x gives me x squared, which is perfect. That's what I need. I also need the L in the FOILing process to give me a -10. So I need a 1 and a 10 there, or a 10 and a 1, -10, +1, -1, +10. Also 2 and 5 need to be considered. And I'm going to consider the 2 and the 5 because they're only 3 units apart. And I need these numbers to add to -3. So I'm going with the 2 and the 5. And I know that +2 plus -5 equals -3, which is my b value. Those are the O and the I terms from the FOILing process. When you FOIL, you have to add those two middle terms together when you combine like terms, and that's the +2x and the -5x. Those will add together here to give us -3x. Again, I know that I factored correctly because I basically just FOILed it out in my head, talked it through out loud to confirm that I did it correctly. Now we can use the zero product principle, set these equal to 0. I'm going too fast. X plus 2 equals 0, x minus 5 equals 0. Solve those little equations. Most of us just do those bits in our head. I'm circling these instead of putting a box around them. Normally I put a box around my final answer. I'm going to circle these because I want to glance up and make sure that they're going to work in my original equation. And you could actually write it out. These numbers are small enough, I think we can do it in our head. If I take the -2 and I plug it in here, this is going to turn into a 9. Square root of 9 is 3. -2 minus 3 is -5, not 1. So we've got a problem. When we plugged in an x value of -2 into our original equation, it failed. It did not satisfy the original equation. Now let's try the x equals 5. If we plug in the 5 to check, and you could be writing all this out and actually write out the arithmetic at the bottom of your notes. I'm just being a little bit lazy. 5 plus 11 makes 16. Square root of 16 is 4. 5 minus 4 is 1. The 5 works. Very messy, very lazy. So it turns out that x equals 5 is our only solution. When we plugged 5 in, when we did a check, it worked, and so 5 is our only solution. When you're working with problems, equations that involve squaring or square rooting, I definitely recommend doing a quick check, even if it's just visually do some arithmetic in your head. But after having done all of this work, you don't just want to throw caution to the wind and pick the multiple choice option that has both of those values, or type them both in separated by a comma and be on your way, because you would have just wasted a lot of time and you'd gotten a wrong answer. Another type of equation is an equation that involves a rational or fractional exponent. And remember that you can take an expression that has a rational exponent and you can represent it or convert it into radical notation, where the numerator of your exponent appears as an exponent on the outside or on the inside of your radical. And when you're solving a radical equation that's of the form x to the m over n equals k, there are two very subtle little sort of things that you have to watch out for. And those are articulated well here. If the numerator of your exponent is even, then ultimately the difference is that you have to watch out for, and you have to use, you don't have to watch out for it, you have to put it in there, is this plus or minus symbol. And that's not a big surprise. If it were x squared equals 16 and you take the square root of both sides, what's the answer? Well, there isn't one answer. There are two answers. It's x equals plus or minus 4. But if it's x to the third equals, what should we use? Let's use 8, and I take the cube root of both sides, the answer is only 2. So there's a great example of where, and you could think of this exponent as 2 over 1, and this exponent as 3 over 1. So that numerator, if it's even, you've got to use plus or minus in your answer. If it's an odd numerator, then you don't. And I like to remember those kinds of rules by relating them back to very simple examples, like this one and this one. Small numbers, basic things that you're already very well versed in and that you're familiar with. So let's see if we can take that and apply it here. In order to solve this equation, I'm going to isolate the x to a power. So let's add 24 to both sides. And then we'll divide both sides by 8. And then we're going to raise both sides of our equation to the 3/5 power. And I'll put a little note about that. So here we are raising both sides to the 3/5 power. 3/5 is the reciprocal of the original exponent 5/3. That's how I chose 3/5. So our answer is x equals 3 to the 3/5 power. Do I need to be including a plus or minus sign in front of it? Let's double check. The original exponent, the exponent on our original expression, was a 5. There's the numerator. In our original expression, the exponent was a 5, and so I'm referencing my notes here, and I see if the numerator of the exponent in my original expression is odd, then I don't need to have the plus or minus. We could express our answer using this rational exponent, or we could write this as 3, and it's being rooted. The denominator of the exponent is the index, so this is a 5th root, and we could take the 5th root of 3 and then raise it to the 3rd power. Now if you have a highlighter or different colored pens or pencils or something like that, you might want to highlight some different components because there are a lot of 3's as it happens. This numerator right here is this outer exponent. And if you want, this 3 right here is this 3, and if you want to just go totally ballistic with this, we need another color. How about this one? The denominator in your exponent becomes the index on the radical. You want to make sure that you know how to make that conversion and get everything into the correct place from exponential form to radical form. Exponential form to radical form. The other option that you have for writing this solution is to take the 5th root of, and you can put the exponent on the inside So you've got 3 to the third now. Let's see if I can find all of my different highlighting colors. The index is out here, it's the 5, and then the exponent is the 3, and all of those were operating originally on the green 3 that I've highlighted here. This gives you the opportunity, an opportunity that the other two formats don't, is here you could write this as the 5th root of 27. And in my opinion, other than leaving it in a rational exponent format, I like this format the best. If it's a choice between these two, which is radical form, I would let go of this one and I would do this one, because you can apply the exponent, the 3 to the 3 in this case, and turn it into a 27. So again, my final answer is the 5th root of 27. Wow, there are a lot of different forms for equations. This little subsection looks at equations that are quadratic in form. We've already talked about quadratic equations. That's true, but look at this ridiculous thing. This has an exponent of 4 and an exponent of 2 and a constant value, which is 9. And what have they done here? They said, well, let's take x to the 4th and write it as x squared squared. And this is really x squared to the 1st power. So you have something squared minus 8 times something to the 1st power minus 9. So the idea is that this exponent of 2 and this exponent of 1, which we don't normally write, makes this look more like a quadratic. Forget that the thing that I highlighted in green says x squared. The recommendation is to use substitution and just write this as a u. Now you've got u squared minus 8u minus 9, and this looks a lot more like a quadratic equation that we're familiar with. And if we slide over, that's exactly what they've written here, and they recommend that we solve this and then go from there. I will show you what go from there looks like. So let's set up this equation by zeroing out one side. Let's move everything over to the left. This 4x to the 4 already has a leading coefficient that's positive. I like that, so I'm going to leave it where it is. We've got 4x to the 4. We'll subtract 13x squared from both sides and add 9 to both sides so that the right-hand side is 0. Then I'm going to use a let statement, and I'm going to say let's let u equal x squared. This is for the purpose of doing substitution. If u equals x squared and I square both sides of this equation, what do I end up with? If I square the left-hand side, I get u squared. And if I square something that's already being squared, I get x to the 4th. Now, I can take the x to the 4th from my original equation and replace it with u squared, and I can take the x squared from my original equation and replace it with u. So let's do that. Let's rewrite our original equation in terms of u. So we'll say 4u squared minus 13u plus 9 equals 0. That looks a little bit more reasonable. I'm not going to say that it looks like fun, but this looks like something I'm more used to. How do I solve this? Go back to the previous section. You've got a lot of options. I wouldn't solve it by completing the square. We could definitely take the 4 and the negative 13 and the positive 9 and plug them into the quadratic formula. or we can solve it by factoring using the AC method. I like the AC method more than I like the quadratic formula. Either one of them will work. I'm going AC on this thing though. A times C equals 4 times 9, which is equal to 36. I take 36, I make my list of factor pairs. That's a 1 and a 36, and a 2 and an 18, 3 and 12, 4 and 9, 5 doesn't work, 6 works, 6 times 6. It's a positive 36, which means either the number on top has to be positive and the number on the bottom has to be positive, or they both have to be negative, so that a negative times negative would make positive 36. Which one of these factor pairs do I choose? As I begin the AC method process, I choose the factor pair that adds to the B value of negative 13. Which pair of numbers is going to add to negative 13? It's this pair, but to get to negative 13, I need both of these numbers to be negative. So that's the pair that I'm choosing. Let's split the middle term. 4u squared minus 4u minus 9u plus 9 equals 0. Could I have written these two terms in reverse order? Could I have written minus 9u and minus 4u? Absolutely. Why did I choose to write it in this order? If you just look at this equation, I put the 4's with the 4 and the 9 with the 9. It's going to make my factoring process easier when I do the next step of the AC method. The next step is factoring by grouping. Factor by grouping. You can write it out. I just wrote the little initials there. Remember, this is our first group, and my second group needs to include the minus sign in front of that 9 there. So I'm being very careful with my under bracketing, and again, don't do parentheses here. Don't use those. Use these under brackets. I say that because if I put parentheses in, this looks like a multiplication problem. I don't want to be foiling here. I'm doing the opposite of that. I'm factoring. So use the under brackets. Okay, factor out the GCF. That's a 4u. I'm reverse distributing. The leftovers are u minus 4. Distribute. I'm distributing in my head to check my work. Yep, that looks good. GCF out of these next two terms. Well, don't forget that my hope is that what's left is going to be a u minus, oh, I made a mistake. 4 times 4 does not equal negative 4. That was wrong. This needs to be a positive 1. So please make that correction. I want this second set of parentheses to be a u minus 1, so what do I need to factor out of these two terms in order to make that happen? And the answer is a negative 9. Then, following the process of the AC method and factoring by grouping, I'm going to take a common factor out of this term and this term. The common factor is the stuff in parentheses. I will leave it in parentheses. That's the u minus 1. The leftovers, 4u minus 9. This is still the same equation, which means the right-hand side of it still needs to say that it's equal to 0. And then we turn the key on the zero product principle. Let's set these two factors equal to 0. U minus 1, u minus 1 equals 0, and 4u minus 9, what is wrong with me? Equals 0, and then we'll solve each of those. I'm circling these because they are not my final answer. They look like they should be final answers, but I'm not looking for u values, I'm looking for x values. Remember that earlier in the process, we did some substitution. We used these let statements in order to change our equation from x's into u's, which made it a little bit more familiar and easier to work with. So now I've got to get rid of these u's. So I'm going to move over here where I've got a little more room to work. And I'm going to back substitute. I'm going to replace the letter u with what u equals. If you want to grab your highlighter again, up here we said that u was equal to x squared, right there. So I will highlight the u's that are down there, this one and this one. We're going to replace those as part of this back substitution process. We'll replace them with x squared. So x squared is equal to 1, and x squared is equal to 9/4. And we're almost done. All we have to do is take the square root of these two equations, square rooting both sides, and we'll have final answers. What is, you can put a little note that you're square rooting both sides and a little note square rooting both sides. What is the square root of 1? Careful. It's not just 1, it's plus or minus 1. And the square root of 9/4? Whatever it is, it starts with a plus or minus. Can I really take the square root of 9/4? I can. I'll square root the numerator and get a 3, and the denominator and get a 2. And what that means is I have 4 solutions. You'll probably need to type those answers in as 4 actual separate values, separated by a comma, if you're entering your answers online. In a multiple choice situation, you might see an option that includes plus or minus symbols. Just be careful as you enter these answers. You did a lot of hard work to get all 4 of those solutions. By the way, I'm not surprised that we got 4 solutions, because the degree of our original polynomial equation, the degree of this equation, was 4. So again, not surprised that we got 4 solutions. Oh good, there's another type of equation. This is an equation that involves the absolute value. An absolute value equation looks like this. The absolute value symbol, many people would describe it as describing the distance of your value from 0 on the number line. I think that's a fine way to sort of visualize it or think about it visually. And in order to work on an absolute value equation, if your original equation says that the absolute value of something is equal to a number, then you need to take that original statement and turn it into 2 new statements, neither of which contains an absolute value. This statement turns into these 2 statements. Your original expression x is equal to the positive version of the right-hand side of your equation, or what was originally in your absolute values is equal to the negative version of the right-hand side of your equation. Let's see a couple examples. So first of all, we have this one. The absolute value of 2x minus 1 plus 3 equals 6. The first thing I'm going to do is isolate the absolute value. I want to get that thing all by itself. All we have to do in order to make that happen is subtract 3 from both sides. Sometimes there will be another number like a coefficient in here outside the absolute value bars. You might have to subtract 3 from both sides and then divide by whatever number happens to be outside of your absolute value. So do what you got to do to isolate your absolute value. We're subtracting 3 from both sides, so we have the absolute value. I don't want to do that right there. Let's move over. The absolute value of 2x minus 1 is equal to 3. and then we'll take this and write it as two separate statements. 2x minus 1 equals 3, so I kept the 3 the same, or 2x minus 1 equals negative 3. Knowing how to start an absolute value problem is key, because, as you can see, I isolated the absolute value, and then I knew that I had to write it as two separate equations, and from there, you know how to solve these two equations. That's not hard. So make sure that your study process includes remembering how to get this type of problem started, because after that, it's a piece of cake. 2x equals 4, x equals 2. 2x equals negative 2, x equals negative 1. There are your two solutions. No sweat. The other possibility that I was thinking was, let's do another problem. I'll say the original problem is 2 times the absolute value of 2x minus 1, close, plus 3 equals 9. Okay, so how do I start this absolute value problem? Well, generally speaking, isolate the absolute value. Remember, that's what we did as we went from this equation to this equation. You should put a little note in there that says, in order to go from here to here, the goal was isolating the absolute value. Clearly we subtracted 3 from both sides, but jotting down a note as to why we did that is an important part of understanding the process and remembering what to do when you're in a new situation. So here, again, we want to isolate the absolute value, so I'm going to subtract 3 from both sides. Nope. There we go. And then, in this problem, we have an additional step to do in order to isolate the absolute value. We have to divide both sides by 2. So now, maybe make these absolute value bars a little darker so you don't get confused and think it's a 1. Now we've got the absolute value of 2x minus 1 equals 3. And what do you know, I've engineered it so it turns out to be the exact same statement as we ended up with here. Still the absolute value of 2x minus 1 equals 3. So the solutions to this problem are going to be the same. Just wanted to highlight for you that you could have that additional preparatory step of needing to divide by something like 2. Wow, that was a lot of different types of equations. Thanks for hanging with me on that. I hope it was helpful, and I'll see you next time.